It's great pleasure to be here and to speak here in the great place for CMB. I like this title because at least in Russia, oh, excuse me, I should, yes. In Russia, a lot of popular scientists are writing that photons of CMB originate on the last scattering surface. And they're coming, and they originate there and coming there. And it's necessary everywhere to explain that this is not true and completely wrong. This is just last scattering. And therefore, excuse me that I'm telling about this simple thing in Princeton. However, I consider that this very principle and very important, and I will tell a few words about history, how we understood that there are two separate separate milestones in the universe. Excuse me, I will be speaking obviously mainly about Moscow, about my interactions with Zeldovich when I will mention history. Obviously, it was very interesting for me at that time. I was very young because Zeldovich was telling something on the seminar, or we were discovering something, and then 3 months, half a year, 1 year later, we were getting preprints from Cambridge or from Princeton or from Harvard or from Caltech, where people were doing the same. And this was very strongly influencing me because, you know, it was forbidden for us to travel. There was a real iron curtain. But, you know, when you saw that people in Cambridge and Princeton are also writing the same, what we wrote, at least in Russia, a year ago, it was great pleasure, and you were understanding that Zeldovich is something very special, and not only 3 stars on, you understand me, for bombs. Yes, let's go further. Excuse me, I'm too long with my introduction. First, next year we will all celebrate, and there will be great celebration here in Princeton, the discovery of CMB. And what is important for all this, my talk, what is important to know only that this CMB is practically isotropic. Everybody here knows this, but our, how to say, let's say now about W map and Planck are so sensitive that we have we see now these tiny irregularities, angular irregularities of the sky, and we are measuring them with unprecedented sensitivity. This is great because when, you know, this was discovered, even dipole, the strongest anisotropy on the sky, was discovered maybe 10 years after, during the flight of U-2 spy plane, which is very, very well known in Russia. When I told that this is great plane, everybody claimed me that I support American spies. I was telling about the measurements of Berkeley group when they discovered this dipole radiation in the universe. But every child knew that this U2 is a bad thing, and we shot it. Yes. Yes. And second very important thing, I don't know why people usually are silent. There is great discovery, another measurement. This is Kobe-Firas. Absolute, this device do not make absolute measurements. And Kobe-Firas was making absolute measurements. And this device, led by John Mather, they were able to measure temperature of CMB with enormous precision. And please understand that just a few years before, well-known and very widely announced Berkeley-Nagoya experiment discovered that there is huge excess in the Wien region, and in the Wien region of in the Wien part of the black body spectrum, there is 25% more energy than in the normal black body curve. And this was, you know, just a few years before Kobe, and then Kobe and Canadian rocket flights showed we are able to measure temperature with precision 1 milli-K, and they were able also to say that there is no any distortions of black body spectrum on the level of 10 to the power minus 5 or 10 to the power minus 4. And this was unbelievably great achievement. And today, I will tell you story, not story, but what we dream. We wish to see additional increase of sensitivity here of spectral measurements, absolute measurements of spectrum for additional 3 orders of magnitude. And it seems that this is possible. Yes. I will speak today about, because these are milestones, I will show you where these milestones are situated. This is a redshift. 0, where we are, 6, where ionization starts or finishes, let's say. Oh, no, not finishes, but where ionization is completely full, let's say so. And somewhere here, we don't know, George Stauffer told in Brussels that value of W map with optical depths of the electrons here is just upper limit. Let us wait additional several weeks and we will see what will be the Planck number if they publish it. Yes, but what is important, this redshift 1100, and here is the last scattering surface about which you all heard many times. But there is another milestone, and this is black body photosphere of the universe at redshift of the order of 2 millions. And this is important because we can observe spectral distortions only after this point in the universe. These milestones, 2 million. And there are several types of distortions. One type, Y-type distortions, many of you here know. This is Y-type distortions. They are observed in clusters of galaxies, and it is possible to, yes, any energy release in the universe creates Y-type distortion after redshift 10 power 4. But at redshift from 2 million to 200,000, here there are very important mu-type distortions, and I will tell you about intermediate type also. But this is important that mu-type distortions are coming to us when universe was really young, younger than 18 years. In Russia, 18 years, this is a lot of songs about girls at 18 years. So it's very special point in the life of the universe. And the last scattering surface, this is 380,000 years, and it's not, I think it's already really good age. Let's go further. Now let us remember 1966, and in 1966, Zeldovich, Ginsburg, and Shklovsky had seminar in Moscow, but Zeldovich asked me to give before on the group seminar review 2 preprints which just arrived. There was real preprint from David Laser from Harvard, and Jeffrey Burbidge sent to Zeldovich only 3 pages, just typed. And these were very important papers because in both papers it was stated that CMB spectrum is just the stellar light thermalized by the dust. Yes, Bruce Drain is here. You see how important was dust from point of view of these people. And at that time, this was enormous. We know today, I just tell you, story should be very short, and story is such that today we know that dust is really very important. Planck demonstrated this. But it's very important on the level of 1 million or 100,000 of the brightness of the black body. It's negligible. But people were very brave. They were telling that it's possible to thermalize dust and create black body spectrum. Obviously, it was very easy to say that there is no so much energy in all stars in the universe to produce CMB. But then I decided to check, in addition, the usual mechanism responsible for black body spectrum production inside hot stars. This is Rosalind free optical depth of the universe. It was easy to compute, to calculate it, and you will find immediately that it's negligibly small. It was 10 in power minus 5 up to redshift 10 in power 8, and even, you know, it was important only, it was becoming important only when a lot of positrons and electrons appeared in the equilibrium with photons. But at the same time, Thomson optical depth was huge. It was, you see, 10 power 7 at redshift 10 power 8. And yes, this is for physicists. That optical depth is probability for a photon to be absorbed or scattered. And this was very, very unusual situation. And I came to Zeldovich before talk and then after talk, and he told me, yes, this is unexpected, that it is so that whole universe is absolutely transparent, and it's necessary to think about the ways, is it in principle possible to create black body, or black body is coming to us just as property of the universe from the beginning. Yes, again I show you this when everything was occurring, and answer is here that it's possible, I will tell you that it's possible to create black body at redshift 2 million. But before, about last scattering surface. It was very easy. Again, there was seminar and I was giving talk where hydrogen will be neutral in the expanding universe if there is full equilibrium. And this was very easy to find, to take the Saha formula, well known, and to find when recombination will occur. And it would occur between 1,300 and 1,000, and very rapidly, exponentially, it's inverse exponents, potential of ionization divided to KTR. It's very rapidly dropping. I gave this talk, and during this talk, friend of mine, Dima Kurt, asked me one simple question. He told me, Rashid, there is recombination. Where is Lyman alpha line? He was, whole his life, he was only observing Lyman alpha line from sun scattered by interplanetary hydrogen. And I told him Lyman alpha line is impossible to observe because nobody can observe in the infrared. It's not important. In addition, it's very far in the wind region and so on. As usual, when you're not preparing, you're telling something. Replying, yes. But then it was absolutely impossible for me to sleep because I thought how Lyman alpha can escape, because expansion is so slow of the universe. And then I was not sleeping 2 weeks, then came to Zeldovich, told him, and finally he told me to check all absolutely processes, even very low probable, in the hydrogen atom. And finally we found these two paper of Kipper, Estonian astronomer, about decay of 2s level in hydrogen atom. Then I recognized that Lyman Spitzer practically simultaneously wrote similar, computed what is the lifetime of 2s level. And lifetime of 2s level is 1/10 of the second. And Lyman alpha, as you know, is 10 power minus 9 of the second. And usually it's, except some nebulae, where very low density, nobody is caring about 2s. When we computed this 2s was 2s, now at present universe, 2s is contributing 2/3 of all recombinations of the universe. 1/3 is coming from the shift of Lyman alpha into distant wind. This is the final result. But this tiny probability is enormously important, and result is huge. Instead, so rapid drop, you have this curve, and here you have freezing out. A lot of electrons were frozen, and for me it was very interesting that collisions between electrons and photons were keeping, and collisions then between baryons and protons and electrons and atoms and electrons were keeping temperature of plasma and of atoms and radiation equal up to redshift 150, and then adiabatic cooling became important and temperature decreased. What is now people are using for 21 centimeters. They think that it's possible to see 21 centimeters absorption because spin temperature will be lower than temperature of CMB. It's very interesting. Therefore, what was main result? Main result is that recombination shifted, you see here, significantly. And second, there is a lot of things. For example, formation of molecules is much easier when we have this frozen fraction of the electrons. This also was very important. But second thing what was very important, because before this computation, we all thought that if recombination occurred, photons here at higher redshifts cannot come to us directly. They are diffusing because mean free path relative to the Thomson scattering is very small, much smaller than the horizon. But when recombination fully occurred, there is no Thomson scatterings and photons are coming directly to us. There is a wall which we see what is painted on this wall. Now, due to this, how to say, very long recombination, we are getting not the wall, but some kind surface. It's the same when we are flying in the plane and see clouds. You see that these clouds haven't boundaries. These are not walls, but we see some diffuse picture. The same is here. We can go further, and with Zeldovich, when we were computing fluctuations and trying to estimate acoustic peaks, we introduced very simple thing, just what will be E minus tau, d tau over dz function, this quasi-analytical solution of recombination, and we found that there is an analogy of last scattering surface. It's like we made approximation with Gaussian, and its position is with precision few percent, the same what is now observed by WMAP and by Planck. Very close, which is understandable because you see this is exponent in power exponent, therefore there is some, it's easy. I can tell you this was not absolutely great achievement. Nevertheless, it was done in reality in '69 when we computed this. Yes, and obviously our English never was enough to introduce so good word as last scattering surface. Therefore, we just write a formula. This wasn't enough. You understand? This demonstrates our level of English at that time. Yes, let's go further. And there are, recombination is producing beautiful things in the history of the universe. And I dream that sometimes they will be, all will be observed. First, there is recombination of the helium plus. Alpha particles are recombining at redshift 6,000. Then at redshift 2,200, helium, normal helium is recombining again. And then hydrogen recombines. And every time we are producing photons and optical depths in the excited Lyman alpha photons, for them optical depth is huge. But if you go already to H alpha, optical depth is small. Second population of second level is very low, and therefore all these photons are in reality leaving. Not all, but many, big part of them is leaving and coming to us. It's possible to observe photons in principle from all these three recombinations. And this is very interesting and beautiful because you can go to the time when your universe was 18,000 years old, 100,000 years old, and finally 260 when photons are coming from recombination, and then visibility function is 368,000, you all know. Yes, and this is a spectrum which we computed with Jose Alberto Rubino Martin and Jens Hluba, maybe more than 10 years ago, and you see all lines of hydrogen. This is Lyman alpha line, which Dima Kurt asked me. It's here. You see Lyman alpha is coming, escaping. This is Lyman alpha, which is escaping through the very distant wing. In reality, now everybody is computing it using Sobolev approximation. It's very interesting that I obviously, but even Zeldovich didn't knew about Sobolev approximation, and we introduced our own way how to find it, and you know everything is in that paper. Now it's a little shame that Sobolev was in St. Petersburg, in Leningrad. It was very easy to learn from him. There is Balmer alpha line, Paschen alpha, bracket alpha, and a lot of other lines. And you see, this is computations, I think, for 500 levels of hydrogen atom and with all transitions. There are also beautiful traces from helium-1 and from helium-2. You see the lines. Hmm?
Those are lines?
These are lines. These are lines. I can, excuse me, because this was more than 10 years ago, I do not remember exactly lines. But these lines also are great because these are forbidden lines. It's not permitted, some of them. And during this work, I was working a lot with helium spectra when I was a graduate student. We thought that it would be possible to see helium lines from the intergalactic gas because density was of intergalactic gas at that time was much higher than today, as you know. Different Hubble constant and omega-1, everything is in baryons. Life was much better, emission measure was higher. Therefore, I was computing a lot of helium spectra, and when I returned to the same problem with Rubino Martin and Jens Hluber, I was shocked. For them, everything was okay. I was shocked because when I was young, transitions between singlet and triplet in helium were completely forbidden. Just no. Now they are permitted. Why they are permitted? Because people like, I consulted with Leonid Weinstein, but a lot of people in Canada did this. Morton did a lot. They computed different things. They were working with helium like iron. It's huge Z. And at high Z, such transitions are permitted. They're low probability that they are permitted. Therefore, when you computed them, then it's possible to return to normal helium, and you're finding what is the probability. And this probability permits you to work. What is this? Oh, excuse me. I do not see it here on this screen. It will go. Okay, it's absent there. Oh, okay. Excuse me. This it was. Now you see real profi is trying, but it's not easy also. Okay. Yes. Yes, and then slideshow maybe. I don't know. Just a slideshow, I think it will go. Oh, good. Thank you. Thank you very much. Yes, and there were a lot of other things, such transitions, and you are learning progress in atomic physics during the last 30 or 40 years is tremendous. Difficulty is only one, that nobody around us is very interested in this. We consider, okay, there are tables, it's easy. But when these changes occurring during your life from completely no, this like mass of neutrinos, Zeldovich always was repeating to me, 0 is beautiful, therefore mass is 0. Then one person made in Moscow wrong experiment, and he immediately told, oh, it's great, everything is not forbidden, it's permitted. And life again was very good. Let's go further. Yes. Now I will speak a little about the distortions of CMB. I'm working in the Max-Planck, Institute, and therefore it's obligation for us to show the face of Max-Planck also. And this is absolutely great thing because Kobe-Firas in reality measured, demonstrated that at that time when they measured spectrum of black body radiation, it was one of the best black bodies. At that time, it was difficult to reach to get so good black body in the lab. Now it's easy. But at that time, it was rather difficult, and these error bars, I've forgotten, are 400 times, I think, bigger than the real error bars, just to demonstrate. And this is the result of these absolute measurements. No spectral deviations. This is the energy density. Everybody knows Planck formula. It's interesting that Mukhanov is very bad person. Everybody afraid when he is in the PhD committee in Munich University, because he is asking people who are doing huge computations of CMB fluctuations of the sky. There are several professors already who were unable to answer his question. And he is asking, please write formula for blackbody radiation. And people are unable. You know, it's absolutely great because they all heard about this, but they are unable to remember. For me, this is very impressive also. Okay, and this is, excuse me, the worst will be if now I will write Planck formula in the wrong way myself. Yes. Yes, this is a Planck formula, you know it, but the best thing is the there is relativistic invariant and this occupation number, phase space density, and nu. And this is a beautiful formula, and it's very easy to work with it in all these problems. And black body spectrum is absolutely unique because it's full equilibrium distribution of photons, and if we know temperature, we immediately know what is the energy density of radiation, and we also immediately know what is the total number of photons. You know, it is 400 black body photons are in the universe just with CMB temperature. We know all that number density of baryons of electrons is much smaller, and we are living in the radiation-dominated universe with huge entropy, very high entropy. Everybody knows this also. And I should remind you that adiabatic expansion of the universe preserves black body spectrum. We don't need any production of the photon or, you know, refurbishing them. They are okay from the beginning until we have the adiabatic expansion. But there are processes, and most important process, I told you how important is scattering, Thomson scattering. And we all know in Landau, in Lifshitz theory of fields, that scattering doesn't change frequency. We have the wave, electrons oscillate in the wave and radiates on the same frequency. But if electron moving with velocity VE, then I have Doppler effect. And then there is broadening of the line. And I can tell you that line is not Gaussian, but line after scattering has this beautiful cusp. This is great, beautiful problem, because you have, here is the angle of scattering enters this formula, and due to enter of scattering, you have different, how to say, different Gaussians for every angle. And for angle equals 0, you have 0 shift of frequency, therefore you have this cusp. When I got this cusp, I was very nervous. How it's possible? Yes. But there is much more important thing, and this, if we go and compute second order Doppler correction, then we find that energy of every average photon after scattering. Here I have plus minus, as you know. Therefore, on average, I have 0 effect. But second order of magnitude effect is 4 times kTe to mc square. It's well known. It's easy to get it classically, in classical way, because this is just Compton drag. If I consider how electron is moving in the radiation field, just using classical formulae, I will immediately find this formula. And it was obtained in the end of the last century, but it was impossible for me when I was learning, was impossible to find anywhere in Russian literature the derivation of this formula. I came to Lifshitz and told, why in your book, Theory of Fields, it's written that it's easy to show. I showed it myself, but it was 12 pages. And Lifshitz told me if I will remember formulae in my books, I will be crazy, go to, how to say, to cellar of our institute. There is a library of Dresden University, physical library as a whole in German. And there are books written in 1912 when physics was finished, everything was done. There you will find derivation. I went and there was really derivation, but 16 or 17 pages. Therefore, everything was okay. Yes, and there is also a well-known, excuse me, there is also well-known term, everybody knows recoil effect. 2 weeks ago, people in Chicago showed me the home of Arthur Compton, who discovered this recoil. There are house of Fermi, house of Compton, house of Millikan. It's enormously interesting just to walk around university. Yes, therefore, recoil shifts us to lower energies, and Doppler, there is diffusion, but on average, it's bring photons up in the energy. And people in the Zeldovich group in Arzamas, where they were working on hydrogen bomb, they discovered this equation. It's named Comptonization equation because Comptonization was a member of the group who was working in Moscow. And this is Comptonization equation, this very important equation which describes really Comptonization in a very good way. And I read many times book of paper of Comptonization, 56. In that paper, everything was easy because they used this was diffusion term, and they knew that diffusion term should give this term 4kT to mh square. Therefore, they estimated immediately what is the form of this diffusion term just to get the Compton drug and diffusion. Then they used very easily found this term, and this term because it was necessary to get wind spectrum. This gave you immediately flow of photons, and like in the river, and this is there is beautiful solution. Also, we found with Larionov, you have here the recoil effect, but it was not written why and what is the origin of the term n square, and this was induced Compton scattering. And I never before heard about induced Compton scattering, and it was absent at that time in the literature. Just completely. Months ago, I was happy. I visited European laser on free electrons. And this is great example that induced Compton scattering is working, really. You saw this. There are two, one working and second under construction. Yes, and I asked Comptonization how they introduced this term n square. And it was easy for me to find it using full kinetic equation, and then, but from Fokker-Planck type equation, and he was unable to say directly. I came to Zeldovich, and Zeldovich told we hadn't time to think, but we knew that this equation should conserve black body, and it conserved black body only in the presence of this term. This was the reason, you know. It was very interesting for me how people thought about this. They were trying to understand that during explosion, temperature will not go very high, and there will be no ignition in the atmosphere or in the ocean. Main idea was this. Yes, and now here I showed you the non-dimensional time, y. It's here, what is y? And y is following thing. It is, in reality, tau, Thomson scattering tau in the universe multiplied to the temperature of electrons of radiation divided per meter square. And this y, small y, describes the broadening and shift of the spectrum or redistribution of photons along frequency axis. In addition, it's necessary for us to introduce another y, let's say capital Y, which corresponds to where you have the temperature of electrons minus temperature of radiation. If you heat or if temperature of electrons is smaller, you are changing the spectrum. You are introducing deviations. And this is physically, they are very different. I have no time to speak, but it's very interesting that if electron temperature is much smaller than temperature of radiation, it's possible to have dynamic Bose-Einstein condensation of photons. There is flow of photons toward low frequencies. And in universe where we have only adiabatic cooling, if there will be no energy release, we will see spectrum which corresponds to this Bose-Einstein cooling of photons. It's beautiful science, but unfortunately, there are sources of energy release which are more significant than this adiabatic cooling. Okay. Yes. Now about chemical potential mu. If we take Comptonization equation and we'll look for is there possible or not to get equilibrium where we do not have fixed amount of photons. For example, I released energy, but amount of photons is the same. I cannot produce new photons. What will be the equilibrium? Comptonization equation shows that with time, I will get distribution of this type. It's very well known in chemical physics. Here I have chemical potential mu, and this chemical potential mu tells me, do I have deficiency of photons, which I will describe you because I ejected a lot of energy, or I will have, how to say, too much photons. And this will be in the case of Bose-Einstein condensation. Given two constraints, energy density, number density of photons, we can immediately find what will be T and mu for any distribution. Most important that its equilibrium, it doesn't change if I do not produce additional photons. But now let us speak about the way how to decrease this mu. And if we know rate of production of photons, even very slow, and energy injection rate, we can calculate evolution of production of mu in T. Let's do this. This is picture of 1970. And you see here the Bose-Einstein spectrum. It is it. And this is a spectrum of Bose-Einstein. And at low frequencies, Bremsstrahlung of double Compton can produce me additional photons and make equilibrium here. Finally, I will get such spectrum. And therefore, we were proposing to look for this minimum in the spectrum connected with deficiency of photons. And what are the two processes responsible for creation of CMB spectrum? First, which everybody knows, it is the process when I have Bremsstrahlung. In the case of Bremsstrahlung, I have proton, electron is coming around and accelerates. When it accelerates, it should radiate photons, low frequency photons. This is Bremsstrahlung. Here, in double Compton case, I have photon which scatters on electron, and then electron has recoil. Electron accelerates, and again it will produce me a lot of low frequency photons. This is double Compton. Formulae are the same in the limit of low frequency, and at low frequencies, probability to create photon is proportional to 1 divided to x squared. But everybody who knows quantum electrodynamics knows this, but it's great that there is also, it's classical process in reality. Even people became interested only in connection with relativistic effects of this. And then when we are producing photons at low frequencies, Compton scattering distributes them over the whole spectrum. We knew about double Compton, but as I told you, life in 70s was much better because density was higher and Bremsstrahlung was stronger than double Compton. In the middle of 80s, double Compton became important because density dropped. Hubble dropped and density dropped. Then double Compton came, and Alan Lightman and Kip Thorne were first to write about this loudly. Yes, even we knew about this. Yes, and what is occurring? How we are creating now black body spectrum? Black body, this is Planck spectrum, and this is Bose-Einstein. You see it? And at low frequency, we are keeping black body again, Rayleigh jeans. And it's coming, these photons here are created due to double Compton and Bremsstrahlung. Then Comptonization takes them here to the maximum of the black body. And slowly we are decreasing mu. We are increasing amount of photons, decreasing mu, and creating black body spectrum. And we with Zeldovich, using this, found that there is very simple formula which is showing how mu is decreasing. Here A is the efficiency of Comptonization, and K is efficiency of Bremsstrahlung of double Compton. And this very simple solution, Danesi and Desozzi put here double Compton and got this very simple formula, how rapidly mu is decreasing at high redshifts. This is black body visibility function, and you see here, this is the black body surface, and if energy, for example, released in 2.5 million redshift, then only 10 or 15% is coming to us of the energy release. If energy is released at 1 million, then 70% of energy of distortion is reaching us. Therefore, we really have some kind of photosphere here, which creates, here is everything becomes black body, and here we see beautiful mu spectrum, Bose-Einstein spectrum. It's bad that we are stopping at 2 million, because you see BBN is here, nothing from BBN, no traces. And even much worse is the electron-positron annihilation. Why electron-positron annihilation is much worse for us? Very important for us, because I think that Peebles was one of the first, Jim Peebles was one of the first people who wrote that in equilibrium, the entropy for pair electron and positron is much higher or significantly higher than for one photon. And therefore, there was a lot of entropy in electron-positron gas, and after annihilation, and after annihilation, all energy and entropy from here went to photons, and temperature increased. And this is the reason why temperature of neutrino is so small, because it remembers what was before annihilation of electrons and positrons. There is also beautiful comptonization, and due to comptonization of electron, of neutrino on the electrons, we have amount of species of neutrino species now 3.046. Usually when I mention this in Russia, people are telling why it is not even, why it is not number, with 3 or 4, why you are telling 3.046. It is just energy and entropy due to comptonization of neutrino on the electrons. But we still have a lot of beautiful things here. We can observe mu distortions from the region of many 100,000 and 1 or 2 millions. And this is silk dumping. I immediately will show you what is the energy. This is the best value of Planck. W map was very close with South Pole telescope, but Planck now gave this spectrum, and this is a spectrum. I can measure whole energy which is released at this time, but I cannot measure what was here. And the cooling, this adiabatic cooling due to Bose-Einstein condensation, it's on this level, but you see the level 10 to the power minus 8, 10 to the power minus 9. Yes, these are solutions, corrections. This is our solution with Zeldovich, term due to double Compton, term due to the Bremsstrahlung. And these are new things with Rishi Hartley, who is visiting Institute now. And precision is better than 1% today. Many people worked here, Burigana, Danesi Desozzi, who in silk were writing papers. Now Jens Hluba is very active in this field also. There are many publications coming. Yes, I told you, most important, there is analytical solution that mu depends, we have the energy release, at any moment, and we have visibility functions. Therefore, we can compute any time what are the distortions. But another type of distortion, completely different. This is Y distortion, which majority of you know because they are observed in the clusters of galaxies. This is Zeldovich. And for me, it's important to mention that this year, Zeldovich, we celebrated, celebrated is not good, but his 100 years, we are living from his birthday. And it's very important, I told this several times in Russia, that he passed away in 2 months, or in a month, there will be 27 years as he died from heart attack. And usually, when person is not with us 27 years, majority of people forget slowly. You know, there is also exponential decay. There are obvious solutions. But I am very happy that his name is alive. And this very rare case, but no, there are giants, but it seems that he is among them. And this is very important for me. Yes, and it was not easy due to several reasons to get street for him. Sakharov has street, and Zeldovich hadn't street. Therefore, I fight it very strongly. And now there is street in Moscow, in very good part of it, which you know, which is Zeldovich, academician Zeldovich Street. Every time when I'm coming to Moscow, I'm looking for the way to drive close or to just to walk there. It's a nice part of Moscow. And in addition, there will be, he had these gold medals, but they all were for first reactor, for Russian, for atomic bomb, for hydrogen bomb. It's not great pleasure to speak about this, but I'm proud that he got street not only due to these things, but also for astrophysics. It was mentioned that also that he made a great contribution to cosmology. I was proud with this. Yes, let's go. And people are observing this, a lot of these, how to say, spectral distortions in the clusters of galaxies. I will mention a little later that there is beautiful frequency here when x is equal to 383, 217 gigahertz, where signal from Compton distortions are equal to 0, is equal to 0. This is very important frequency for Planck, because Planck measuring effect at different frequencies and is able to find what are the Y distortions. Its spectrum is so strongly differs. It's very important. And these are Planck old data. It's certainly now it's already, I already saw the fire. It seems practically final paper with new catalog. There will be even more clusters from Planck than on this image. It's significantly more than 1,000. Yes, but I am very impressed by this plot from SPT group, from South Pole Telescope group. Red, these are Planck clusters. Blue, this is all what was possible to find from Rosatoll Sky Survey. And black, these are data from SPT, and green from Atacama Cosmology Telescope. And you can see that Atacama Cosmology Telescope and SPT are observing. These are practically all. Planck mainly observes well-known clusters, and Atacama Cosmology Telescope is discovering clusters, and SPT, they're discovering clusters just on the blank sky immediately. And plans are huge because this is done with 3,000 bolometers, and both David Spergel and John Karlstrom are telling us now that very soon there will be 16,000 bolometers in the focal planes of these instruments, working in 3 different colors. This is your 4, 3, 5. 5 different colors. They will measure. It's great. But SPT is telling me only about 4. You have 5. What could you tell us frequencies? 90? Oh, 30, 44. Also bolometers for 30. No, okay. This I have 30 and 45. Okay. Excellent. And then they are dreaming now about 150,000 bolometers in the focal plane of this telescope, and Argonne is working, producing now this telescope. This is enormous progress, and I was in reality very unhappy in Brussels because both David and John were doing everything what is possible to say that the next mission, space mission to measure polarization and angular fluctuations is not necessary because they will do everything from the ground, at least as I heard. But then you told important thing I will refer, but before it was that we can do everything from the ground. It was very impressive. Now I will speak with you. A lot of experimentalists are telling me, are you sure that we will distinguish mu distortion from Y distortion? And this is the spectrum prepared with, from our paper with Rishi Hartree. You see here, this is the Y distortion. And you see in the Y distortion, this is frequency 217 gigahertz, where it crosses 0. And this is mu spectrum, and mu spectrum is crossing 0 at 124. I have no time to describe how we are getting this 124. This is just linear expansions. Temperature of photons, temperature of electrons in the field of Bose-Einstein spectrum is 1 plus 0.454 mu. And then if you expand the spectrum, you are getting that for Bose-Einstein spectrum, it will have 0 at frequency when x is equal h nu to kTe, and frequency is exactly 124. It's possible, and Rishi showed this in separate paper, that it is rather easy to distinguish between these two spectra. But the situation is even more interesting, and it's more interesting because there is intermediate region. And we computed what will be the intermediate spectra, starting with Y spectrum. We were increasing Y parameter and coming to the mu. And any energy release at different Y or a different redshift will give us different spectrum. And this is much more interesting because observing such spectral deviations, you can say not only how much energy was released, but you can measure also when it was released. For example, if there is decaying particle, you can say what is the lifetime of the particle. And this is new window here, and we can get a lot of additional information because Y and mu are much worse. At high redshifts, you have only mu, and you cannot say exactly when energy was released. At small redshift, it's only Y-type distortions, and you cannot say when energy was released. Yes. Now, I should mention to you that there is huge, great progress in the technology of experiments, and especially of detectors. Improvement was during, after 77 orders of magnitude. There are many theoretical models predicting significant energy release in the early universe. But I will speak now only about unavoidable spectral distortions, because every experimentalist with whom I am speaking, they are telling, Rashid, we will observe, and we will provide only upper limits. We don't like to produce only upper limits. We should discover something. And therefore, now I am showing them, you will certainly discover the spectrum of recombination. You will certainly discover the silk dumping. You will certainly discover this, if you will achieve level of 10 power minus 8 of black body. And I remember that during maybe last 10 years, every year when meeting John Mather, I was asking him the same question. Please tell me, if you will get money, what sensitivity, how much you will improve sensitivity of COBE. And he always was joking until there is James Webb telescope is there, nobody will give me money, which I think that it's true. But finally, in Venice, during the conference, 100 years of cosmology, he told, okay, we can do this 100 or 1,000 times better. And he gave talks there, and this was beautiful. And after that, his team proposed PIXIE. And this was great step in reality. But before, I wish to tell you additional thing, that CMB, this is CMB spectrum, and these are primordial damping. This is old picture, but with Planck it is the same. And you see that after L3000, this is different processes. These are foregrounds dominate. This in reality also Y okay, Z distortions, but you see them. And this is the change. We cannot go more farther than 2000 or 3000, investigating the spectrum of primordial fluctuations. And here you see it in different way. This is a silk damping. This is angular resolution of SPT and ACT. And this is undamped, without viscosity, without thermal conductivity in the universe. There will be this level of, how to say, prolongation of the CMB angular fluctuation power spectrum. In reality, we do not have nothing. There is only energy injection. And this energy injection will produce as mu-type distortion, intermediate, and Y-type distortion. That we can say immediately what level of energy release will be if spectrum is as we think today. These are two proposals. Both are till now not approved. It's PIXIE, this European prism, now core, but both of them are very sensitive. And you see what is the title of, what's the name of PIXIE. And you see here also people from audience. But this is what they will do. Why instead of 10 power minus 5, 10 power minus 8? They will be measuring. And mu, this is a level 5 times 10 power minus 8. They also dream to measure. They're telling that they will do this. And I can show you if this is a spectrum of today limits. This is K for power spectrum. This is the level of PIXIE, this level of prism. You will detect what is this is the best CMB fits. If, for example, spectrum goes here up, we will detect this. We will detect even present level. What Mukhanov and Chibisov formula is giving, we can easily find this. Okay, now there are additional energy releases. First is electron-positron. I told you that this is electron-positron annihilation, provides us more than several times energy of the photons. Nevertheless, this is Rishi computed that final result will be 10 to the power minus 178. I proposed to put 180. He told that our formula has higher precision. Okay. Yes. Now then there is BBN tritium decay. It's only 10 to the power 15, but it's yes. If we will be able to measure the neutrino temperature in the best way, we measure total energy. Yes, total energy. I agree with this. Yes, I agree. But we do not measure directly huge energy release. Yes. Then there is I like also beryllium-7 decay, this energy release when it produces lithium-7. You all know that lithium-7 is not produced during BBN. It's beryllium-7, and at redshift 20-30,000, there is capture of internal electron, and we are producing beryllium-7. Here, but this process produced two narrow lines in the neutrino spectrum. It will be possible to see if there are WIMP dark matter annihilation. It will be possible to measure it. Silk dumping is the most important thing. And there are many other processes I will not even mention. Now people, there are every 2 weeks, paper appears about new energy release source. Most important for me is that PIXIE is telling us that on the level of 5, 6 sigma, they will detect hydrogen lines. This is great. But there will be additional very important projects. We are working now with Jean-Loup Puget discussing. This is the following. You all know about scattering due to ionization. But there are well-known ions like C1, carbon-2, nitrogen-2 lines. Everybody knows these lines. And these lines are also scattering primordial peaks and destroys them. Therefore, if you measure, and you know in all Planck channels, and can compare what is the amplitude of the peaks in different frequencies, it is possible to give upper limit to the abundance of the heavy elements. And these upper limits, today, what is rather easy to get will be on the level of few times 10⁻⁻�3. It is what we are checking now numbers with Planck, and maybe this will also, it will be possible to do also with several frequencies on SPT and Atacama Cosmology Telescope. Thank you. Excuse me, I was a little long.